Today, we will be exploring the power of artificial intelligence, 5 ways neural networks are revolutionizing visualization. Neural networks have become increasingly potent tools in recent years that are transforming visualization in many different disciplines. Neural networks have demonstrated amazing skills to extract patterns and insights from complicated datasets in a variety of applications, including image recognition and data analysis. Without further ado, let's begin. Number 5. Interactive real-time visualizations. Neural networks are essential for real-time interactive visualization because they improve system speed, flexibility, and responsiveness. Recurrent neural networks (RNNs) and deep reinforcement learning (DRL) are two methods by which these networks enable dynamic interactions between users and visible data in a variety of applications. Systems that interact with their surroundings can learn the best course of action thanks to deep reinforcement learning (DRL) methods, a subset of machine learning. DRL algorithms can drive interactive visual systems in which users can change visual elements and get real-time feedback depending on their actions. When users modify parameters or filters in interactive data exploration tools, for instance, DRL algorithms dynamically update visualizations in real time to reflect these changes. This feature promotes deeper insights into complicated datasets and increases user engagement. Because they can process sequential data, recurrent neural networks (RNNs) are another family of neural networks that perform well for real-time visualizations. RNNs are able to assess incoming data streams constantly and produce visuals that adjust to changing trends or patterns, making them useful in applications like financial market monitoring and live streaming analytics. Decision makers are better equipped to react quickly to shifting circumstances and make well-informed choices thanks to this real-time analysis. In general, real-time interactive visualizations made possible by neural networks improve user experiences and allow for more efficient analysis and decision-making in a variety of fields, including corporate intelligence, scientific research, gaming, and entertainment. We should expect more developments in real-time visualization capabilities as neural network techniques continue to mature, creating new avenues for immersive and interactive data study. Number 4. Natural language understanding and text display. Natural language processing (NLP) has advanced significantly thanks to neural networks, which have also transformed text visualization methods and made it possible to analyze and comprehend textual data more effectively. Textual data can be converted into high-dimensional vector representations using neural network models, such as word embeddings and transformers, which makes semantic analysis and visualization easier. Words from a lexicon are mapped to dense vector representations and continuous vector space via word embeddings, including word2vec and glove. More sophisticated analysis of textual data is made possible by these embeddings, which capture the semantic links between words. Semantic similarities and differences between words or documents can be examined by visualizing these embeddings using methods such as principal component analysis (PCA) or TSNE. This helps with sentiment analysis, topic modeling, and document clustering, among other tasks. Further advanced text visualization capabilities are available with transformers, especially with models such as BRT bidirectional encoder representations from transformers and GPT generative pre-trained transformer. By capturing the contextual relationships between words in a sequence, these models allow for more precise language production and processing. Users can help with model interpretation and debugging by using approaches like attention visualization, which provide insights into the textual elements that have the most influence on the model's predictions. Neural network-powered text visualization approaches are useful in a variety of fields, such as market research, social media analytics, and content recommendation systems. Sentiment analysis tools, for example, assist organizations understand consumer sentiments and market trends by visualizing sentiment trends across time. Similarly, topic modeling visualizations help academics explore big text datasets and find significant themes by offering insights into the distribution of subjects within a corpus. In general, text visualization has changed as a result of neural networks, becoming more user-friendly, interactive, and educational. We may anticipate more developments in text visualization methods as NLP research moves forward, providing better insights into textual data for a wider range of applications. Number 3. Models that generate creative visualizations. A new era of creative visualization has been brought about by neural networks, namely generative models such as variational autoencoders (VAEs) and generative adversarial networks (GANs). These models are redefining a number of creative industries, including entertainment, design, and the arts, because of their amazing capacity to provide original and lifelike data samples. Generative adversarial networks (GANs) are composed of two neural networks playing a competitive game, the discriminator and the generator. Whereas the discriminator learns to distinguish between actual and produced samples, a generator learns to produce synthetic data samples like photos that are identical to genuine data. By using this adversarial training process, GANs are able to generate extremely lifelike text, audio, and images. GANs are used by designers and artists to produce innovative works of art, realistic textures, and even remarkably lifelike synthetic faces. Another family of generative models that can be trained to encode and decode high-dimensional data distributions are variational autoencoders (VAEs). By learning a probabilistic latent space representation of the input data, VAEs make it possible to create fresh samples that are similar to the distribution of training data. Because of this feature, VAEs can be applied to a variety of activities including creative exploration, anomaly detection, and data augmentation. VAEs are used to create new ideas and explore the wide range of creative possibilities in industries like fashion design and architectural modeling. Because generative models have made it possible for artists, designers, and other creators to explore and experiment with new ideas in previously unheard of ways, they have democratized creativity. We expect more advancements in creative visualization methods as generative model research advances, which will result in fresh approaches to artistic expression and innovation in a variety of fields. Are you still there? Perfect, go ahead, subscribe to our channel and like this video. Let's continue. Number 2, interactive analysis and exploration of data. Neural networks offer straightforward tools for visualizing high-dimensional data, which makes interactive data exploration and analysis easier. It might be difficult for analysts to derive significant insights from complicated datasets with lots of variables when using traditional visualization techniques. Nonetheless, by lowering the dimensionality of the data while maintaining its underlying structure, neural network-based techniques like UMAP uniform, manifold approximation and projection, and TSNE distributed stochastic neighbor embedding provide answers to this issue. Neural networks are used in TSNE and UMAP two-dimensionality reduction methods to project high-dimensional data into lower-dimensional environments, usually 2 or 3 dimensions. These methods are ideal for visualizing clusters, patterns, and outliers in complicated datasets because they maintain both the local and global links between data points. Analysts can more easily explore and comprehend the underlying structure of the data by displaying it in lower dimensional areas. Neural network-powered interactive data exploration tools allow users to dynamically change visualizations by changing parameters, focusing on certain regions, and investigating correlations between variables in real time. By enabling analysts to find hidden patterns and correlations that may not be seen with static displays, this interaction improves the analytical process. Furthermore, the integration of other data modalities such as text and images is made easier by neural network-based visualization approaches, allowing for Number 3, models that generate creative visualizations. A new era of creative visualization has been brought about by neural networks, namely generative models such as variational autoencoders (VAEs) and generative adversarial networks (GANs). These models are redefining a number of creative industries, including entertainment, design, and the arts, because of their amazing capacity to provide original and lifelike data samples. Generative adversarial networks (GANs) are composed of 2 neural networks playing a competitive game, the discriminator and the generator. Number 1. Improved classification and recognition of images. Convolutional neural networks, CNNs in particular, have revolutionized image identification and classification jobs by greatly increasing accuracy and efficiency. CNNs are excellent for deciphering images with intricate structures and patterns since they are specifically made to learn hierarchical representations of visual input. CNNs have made significant advances possible, one of which is their automatic feature extraction and learning capabilities from images. The capacity to capture intricate visual patterns was constrained by the handcrafted features that were frequently used in traditional computer vision approaches. On the other hand, CNNs do not require human feature engineering because they can learn hierarchical representations of features straight from raw pixel data. This allows them to be used to a variety of visual applications. CNNs learn by putting images through a series of convolutional and pooling layers that gradually extract features at a higher level, like edges, textures, and object components. The network's classification layers then utilize these learned attributes to forecast the image's content. Pre-trained CNN models can be further refined on certain datasets using methods such as transfer learning, which enhances the performance on specialized tasks. CNNs are widely used in many different sectors for image identification and classification, such as autonomous cars, satellite imaging, surveillance systems, and medical imaging. CNNs are used in medical imaging to accurately diagnose diseases using X-rays, MRIs, and CT scans, supporting medical practitioners in making clinical decisions. In a similar vein, CNNs and satellite imagery help with urban planning, disaster monitoring, and land cover classification, while offering insightful information for resource management and environmental monitoring. All things considered, CNNs have transformed picture identification and classification by making it possible to provide more precise, effective, and scalable solutions for a wide range of applications. We can anticipate more breakthroughs that will push the limits of what is feasible in visual understanding and analysis as neural network research advances. Time to wrap up the video. If you liked the video, don't forget to share it with your loved ones. Goodbye.